Hello class, welcome to lecture 9, and in this lecture we're going to be taking a look at something called kinematic flow patterns and talk about what exactly we mean by kinematic flow patterns and take a look at some basic examples of kinematic flow patterns. But first off, let's go ahead and introduce what exactly we mean by a kinematic flow pattern. So, excuse me, kinematic flow pattern, what we mean by that is we're talking about a flow pattern that has no specific time dependency. So it doesn't depend on time. It's more or less just a snapshot view of something that's happening at a particular point in time, what the flow pattern actually looks like at a particular point in time. So since there's no specific time dependency, that means that there is no acceleration in the strictest definition of acceleration. So acceleration is change in velocity with time. Since there is no time dependency, there is no acceleration. That said, the flow velocity can change in the x, y, and z directions, but the flow velocity will not change it will not change with time, but it can change through space. So as we go from maybe from the west to the east, the flow might be increasing, but we're not talking about something that's increasing as time goes forward. And let's also take a look at some examples, one of which we actually looked at in the previous lecture when we derived the mass continuity equation and took a look at something called horizontal divergence. In fact, divergence/convergence, strictly speaking, this is divergence, but you can also think this as divergence and convergence. That is one example of a kinematic flow pattern. And you can see that there's no specific time dependency here. Here it's just a derivative of the zonal wind with respect to x and a derivative of the meridional wind with respect to y. So there's no time dependency in there at all. But as we saw in some of the previous lecture, you can have zonal and meridional wind components that are changing as you go in the x direction and or in the y direction. But this is not the only kinematic flow pattern that we can have. Another one that's really important in the world of the atmosphere, especially if you like tornadoes, and that is the idea of vorticity. And that'll be the subject that we'll talk more about in the next segment. And I believe also we'll talk about this example in the next segment as well, which is called a deformation pattern. And there's actually, technically, there are two separate deformation patterns, but they are pretty much the same thing. And we'll talk about what exactly we mean by vorticity and deformation patterns, and that'll be something we talk about in the next segment. But for now, I just want to introduce give a broad overview of what exactly we mean by kinematic flow. And I also want to go ahead and contrast that while we're on the subject. I want to contrast that with the opposite of a kinematic flow pattern, which is a dynamic flow pattern, and also streamlines, which we won't talk about in this lecture, but it will be a topic in the next lecture. But now I do want to sort of talk about the idea of a dynamic flow pattern. Now, kinematic, there's no specific time dependency, but for a dynamic flow pattern, now you're talking about something that does have time dependency. So this might be looking at how a flow pattern evolves through time, which means now we can actually introduce acceleration into the equation when we're going to look at a dynamic flow pattern. But for now, we will talk a little bit about this later on, but for now we're going to focus on the kinematics. But again, I just sort of want to give you an idea of what exactly we mean by kinematic versus dynamic. So some examples of this, of a dynamic flow pattern, might be a partial trajectory, and we'll also talk about that. Partial trajectories and streamlines kind of go hand in hand, but they are different, and the difference between the two is primarily that time dependency or lack thereof. And then something else that we talked about is Ekman pumping. So if you've got a force imbalance, that means you've got something that is accelerating, so that means it's evolving with time. And the whole idea behind Ekman pumping stems from what we looked at in lectures 6 and 7, where introducing the idea of friction, or introducing friction into our force balance at ground level, cause the winds to accelerate towards the center of cyclones and decelerate away from the center of anticyclones. Since you've got a force imbalance there, you've got flow that's accelerating, which means you've got a time dependence, which means you've got a dynamic flow pattern. And again, the term for winds converging at the surface and then moving upward, the term for that is Ekman pumping. So that's just sort of clarifying what exactly you mean by here. But any sort of force imbalance results in an acceleration, which therefore results in a time-dependent flow pattern. But I just wanted to introduce those two concepts, and in the next segment we'll take a look at vorticity and deformation and actually take a look at some of the mathematics behind all this. So with that, I will see you all in the next segment.